Here, before we begin, I wanted to mention I got an email from Badur, uh, who forwarded something from the Kent State software people. So apparently, uh, she was not able to install Mathematica because the Kent State site license has expired and they're still working on renewing it. So have any of the others of you had this problem also? No,
Yeah, I haven't been able to get
you
mine.
haven't. So you told me you requested a license, you were waiting for an email, right? And you didn't get one, right? So
Yeah.
I guess Badur had the same thing, and so she inquired about the missing email, and this was the response that she got. Um, um, What about the others? Is there anybody here who was able to install it recently? Yes, Alan. Okay. So you downloaded it and installed it, and that's since the semester began?
No, I've had it like almost a year. I haven't really used it, but I downloaded it like last year at some point. I saw that we could get it.
Okay.
So I've had it for a
Okay.
while.
Okay.
If I might
And
interject, Professor, I was,
Chris, I'm sorry.
if I was able to install it this semester at the beginning.
You
of the
were
semester.
able to install it this semester. Huh. Well, I'm so confused. I don't know what's going on. Chris, did you do it in just the regular way that I had on that syllabus?
Yes, sir. Followed your syllabus, got the link, and everything went in fine. It did have a weird expiration date of the 21st of this year, of last month, but I was able to put everything on, no problems.
Well, I don't know. Maybe it depends on exactly which day people did things, right? Maybe, there was a particular day when it stopped working just, a few days ago. Okay, so there's a minor problem and a major problem. Okay, so the minor problem is that you guys, or at least some of you guys, are unable to install this. And so for that, let's just say, let's wait until Kent State fixes this thing. And I don't know when they will, but I trust they will sometime soon. So for the moment, I will say that the Mathematica homework problem is optional. So you don't have to do that one. If you have downloaded it and you want to do this problem, sure, great, go for it. But if you have any problems with getting the software installed, just don't worry about it. And you do not need to go into the Kent State Library to use the Mathematica they have installed in the library. I don't want anybody to do anything that they think is risky for their health just in order to do this. It's not that essential. Okay, so just don't worry about that. Okay, the major problem is that my Mathematica is going to stop working sometime soon if Kent State doesn't finish this. And I totally depend on this thing. I use it every day of my life. And so I don't know what I'm going to do if it stops working. So we'll figure out about that. Okay. That's all I can say about software licensing. That is beyond my capability. But let's go back to physics. Now, let me refresh your memory about what we're working on. Okay, so we are trying to solve Schrodinger's equation. Okay, so you remember we have the equation of this form that IH bar d psi dt is this, minus h bar squared over 2m times the second derivative with respect to x plus v of x times psi of x and t. Okay, so this is a partial differential equation, right, which depends on two variables, x and time. How do you solve it, right? Well, we were considering the method of separation of variables. That is, we assume that there is a special solution of the form that this function of x and time is some function of x times some other function of time, okay? And most solutions are not like this, right? This is a special kind of solution. And the word for this special kind of solution is a separable solution. Most solutions are not separable, but a few solutions are separable. So let's try to figure out at least the separable solutions. Okay, so what we did then was to plug this assumption into Schrodinger's equation. And then you could see that it breaks up into one equation for time and one equation for x. Okay? And the equation for time is actually something that was exactly solvable and it was not too hard. Okay, and so the time equation gives us that phi of t is the exponential of minus I e t over h bar. Okay, and then the position equation is the hard one that we're going to work on. Okay, so the position equation turns into saying that the Hamiltonian operator acting on this lowercase psi is equal to E times the lowercase psi. So this equation is what people call the time independent Schrodinger equation because we've already gotten rid of time from it. And the E here has to match the E there. It has to be the same number. And let's see, so this thing is the Hamiltonian operator, meaning the total energy. And that is minus h bar squared over 2m times a second derivative with respect to x plus v of x. Okay, so we don't have an answer yet. We don't have an answer yet because we don't have a specific question yet, right? We haven't said what the potential is, right? So far, this is general considerations that work for any potential energy function, v of x. Okay. And then at the end of the last class, I was talking about some special properties of separable solutions. Okay, and there are a couple special properties that I mentioned. One is that they are stationary, meaning that if you get the probability density that is this psi star times psi. The time part of that just cancels. That's the lowercase psi of x e to the I e t over h bar times psi of x e to the minus I e t over h bar. And oh boy, that cancels. Okay, so this is independent of time. Furthermore, all expectation values are independent of time. So that's a remarkable property, which we might not have expected. And so that means that, you know, another word for this special class of solutions would be stationary states, right? We could call them separable solutions or stationary solutions or special solutions. You know, those words mean about the same thing. Okay, and then another feature has to do with the expectation value of the Hamiltonian. Okay, so the expectation value of the Hamiltonian, that is to say, the expectation value of the total energy okay, so that's this integral sandwich of psi star h psi dx. But the thing that I showed you at the end of the last class was that this h psi, well, that's equal to e psi in any of these special solutions. And then the e we can just factor out of the integral. So it's e times this integral of psi star psi dx. Oh, and that integral is equal to 1. That's the normalization. So this is just equal to E, okay? So E is for energy, right? And so the E is the expectation value of the energy, the average energy in this state, okay? Now, what I ran out of time with last time is that we could say, well, what's the uncertainty in the energy, right? What's the standard deviation of the energy? Well, if we want that, we need to get out what's the average of the Hamiltonian squared. Okay. So that's this integral of psi star h squared acting on psi integrated over x. So h squared means you apply the Hamiltonian operator twice. So psi star h psi dx. Okay. Now we know what is h psi. That's e psi. Okay. So we can factor out this energy E. So now there's this integral of psi star h psi. So here's the second of the h's. Okay, but this h psi, this is also E, right? So we get two factors of E. times this integral. So this is just E squared, okay? So the average of energy squared is just E squared, okay? So then we could say the uncertainty in the energy standard deviation sub E, or maybe standard deviation sub H would be a better term for it. The uncertainty in the Hamiltonian, that is the average of H squared minus the average of H, quantity squared. Okay. That's E squared minus E squared. Oh, that's 0. Okay. So in one of these states, there is no uncertainty in the energy. In a separable state. Okay. That's not normally true, right? So normally in any generic state, there is some uncertainty in the energy, okay? But not in one of these special states. That's a special feature of the special state, so that there is a specific energy. Okay. And then I guess the last general comment I can make, right, is that a general solution, okay, comment number 3, a general solution is a linear combination of special solutions. So this is the kind of thing that you might have seen in an E&M class, right? So in an E&M class, if you're solving for, let's say the electrostatic potential, you might do separation of variables in Cartesian coordinates. And you could get special solutions in some function of X times a function of Y times a function of Z. Right? And then the general solution is adding up a whole bunch of the special solutions. Okay? And so the special solutions are solutions where the Hamiltonian acting on psi1 is equal to E1 times psi1. The Hamiltonian acting on another state, psi2, is equal to E2 times psi2. The Hamiltonian acting on psi3 is equal to E3 times psi3. Okay, so you see here are 3 special solutions, right? There might be an infinite list, right? And so it's the same Hamiltonian operator acting on different psis gives different energies times the psi, okay? So state psi1 has energy E1. State psi2 has energy E2. Psi3 has energy E3. Okay. So that means they each have their own time dependence, okay? So with state 1, the time dependent wave function is this lowercase psi1 of x e to the minus I E1t over h bar. And likewise, the time-dependent psi2 is this lowercase psi2 e to the minus I E2t over h bar. And the same for psi 3. Okay. So they each have their own time-dependent exponential factor, okay? And then the general solution is a linear combination of these things, okay? And it's a linear combination, meaning it's a sum of these different states, each with some coefficient. All right, so it's a sum over lots of different values of n of some coefficient Cn times the state number n. So psi n of x exponential minus I E n t over h bar. So this is a general solution. And the point is, this solution satisfies Schrodinger's equation. And it satisfies Schrodinger's equation because Schrodinger's equation is linear. So that's a special mathematical feature of linear differential equations, right? So linear means that in the differential equation, everything is linearly proportional to psi. Okay? The dependence on x might be more complicated. The dependence on time might be more complicated. But everything is linearly proportional to the wave function psi. Okay? And a remarkable feature of linear differential equations is that if you have two solutions and you add them up, it's still a solution. Right? Or if you multiply by anything, it's still a solution. Or if you add up 100 of them, it's still a solution. Okay? That is true only for linear differential equations, not for nonlinear differential equations. Okay? But Schrodinger's equation is linear, and so we can add up solutions in this form. Okay? And so, once we generate a set of special solutions, these things, then we can combine them in this way and get a general solution. So it's a whole family of solutions with any old constant coefficients that go in here. And if we combine the solution in this way, then what we get is this general solution. Any arbitrary solution can be expressed this way. And then this thing is not stationary. And it does not have a definite energy. It doesn't have those special features because this solution is not the product of some function of x times a function of time, right? It's the sum of a whole bunch of things that look like products like that, but it's not in and of itself a product like that. Okay, so that is a whole bunch of general points, okay? And now these things all become more interesting when we apply them to a specific example. So, let's actually do an example. All right, so I want to get started today by solving Schrödinger's equation for one example. Okay, and the example that I will start with is what I will call a particle in a one-dimensional box. And this is the same thing that is in the textbook, but in the textbook, there's a different name for it. The textbook, this is in section 2.2, and they call it the infinite square well. Okay, so the idea here is that there's a particle that can be anywhere between x equals 0 and x equals some a. But it cannot be outside. Okay, so it's a one-dimensional box, right? It's a box that goes from x equals 0 to x equals a. Right, so the particle can be anywhere in between, but it cannot possibly be outside for any other value of x. Okay? So we could represent that by a potential energy, which looks like this. Okay, so we could say if we want to draw v of x as a function of x, there is a hard limit at x equals 0. And there's a hard limit at x equals a. So the potential energy goes to infinity there. So you can't possibly be outside of this range. Okay, but the potential energy is 0 in between. So we could write that as v of x equals 0 for x between 0 and a, and v of x equals infinity otherwise. So in the textbook, when they call this thing an infinite square well, okay, infinite means the potential goes up to infinity, okay? And square well means that it's a right angle here in the potential energy plot, okay? It doesn't mean that the box is a square because this is one dimension. There's no square in one dimension, right? And so the square well just means, these are square angles, I guess, in the potential energy plot. Okay, so the important part about saying that the particle cannot be outside is that it implies, it implies that psi equals 0 anywhere outside. Okay, so the wave function has to be 0 everywhere that's not inside the box. And then inside the box, the wave function is some complex number. We want to figure out what it is, okay? But whatever it is, it has to go to 0 at the edge of the box so that it can be continuous, right? So right at the edge of the box, it goes to 0 and then it stays 0 everywhere outside. Okay, we're good with this? Okay, it was just what the problem is. So now let's solve it. Okay, so we have the pieces now that we need to solve it. Okay, so first of all, we have already broken the Schrodinger equation into the time part and the time independent Schrodinger equation. So for the time independent Schrodinger equation, okay, that is H psi equals E psi. Okay, so H psi is minus H bar squared over 2m times the second derivative with respect to x plus V of x, psi of x, and that has to equal E times psi of x. Okay. Now we need to put in the potential energy. Okay. We know that the potential energy is 0 everywhere inside the box. It's infinity outside the box. Okay. But we don't need to do anything outside the box because we already know that psi is 0 there, right? What we're trying to do is figure out what's the wave function inside the box. And so here, this is V equals 0 inside the box. Okay, so inside the box, we only need to solve minus H bar squared over 2m times the second derivative of psi with respect to x is equal to E times psi. Okay. So this is just a differential equation for a function of one variable. Okay. And it says that the second derivative of psi with respect to x is negative 2me over h bar squared times psi. Okay, so what's the solution for a differential equation like this in the region for x between 0 and a? Okay. Our normal trick for solving differential equations, if we can, is to see if we can just recognize the differential equation and see if that's similar to any equation we've ever worked with before. Has anyone ever worked with an equation like this before, where the second derivative is negative something like something times the function itself? Okay, so Andrew, what have you seen like this before?
Where have I seen it? But it's sines and cosines or whatever.
Sines and cosines, sure. Okay, and that's exactly right. Okay, and so to make it look even clearer, right? We could say let's define this thing to be some parameter. Let's call it k squared. Okay, so let's let k be the square root of this thing. Okay, so the square root of 2m e over h bar. Okay, so the differential equation is second derivative is minus k squared times psi. Okay, so the solution has to be sines and cosines. And sines and cosines of what? Well, just k times x, right? So we'd say psi of x has to be something times the sine of kx plus something times the cosine of kx. So this is a solution if I have any constants in those blanks. Okay, so let's call these constants capital A and capital B. So, you can check if you take the second derivative of this function, right? In the first term, you get, in the first term, you get minus a k squared sine kx. In the second term, you get minus b k squared cosine kx. And oh, sure enough, that's minus k squared times the function itself. Okay, checks out. All right, so this satisfies the differential equation. Okay, but satisfying the differential equation is not enough. Okay, we also have to satisfy the boundary conditions. Okay? So how about the boundary conditions? The boundary conditions, I claimed before that psi goes to 0 as x goes to 0 and at x goes to a. Okay, so that means that psi of 0 equals 0 and psi of a equals 0. Okay, so that's two conditions that both have to be true. Okay. Let's do the one at 0 first. Okay. So this equation tells us, let's see, psi of 0, that is a times the sine of 0, that's 0, okay, plus b times the cosine of 0, that's 1. Okay, so psi of 0 is just b. So that has to be equal to 0. Oh, okay. So that tells us that the parameter b has to be 0. Okay. So based on that, we could say, well, psi of x is just a sine kx. Okay. So when we include the boundary conditions, the equation has to be just a sine. But so far, a can be anything, and k can be anything. Now let's do the second boundary condition. So the second boundary condition is that psi at position A is 0. So that means that capital A times the sine of k times little a equals 0. So either a is 0 or the sine of little k times little a is 0. Okay. Well, if capital A is 0, that means that our solution is just 0 everywhere. The casual thing I could say is that's no solution. Right? That's just saying, there's no wave function. It's always 0. A fancier way of saying the same thing is that this is not normalizable, because if I try to calculate the normalization integral, it's 0. And so, if I need to divide by something to normalize that, I need to divide by 0. Well, that's not going to work. Okay, so forget that. So this is no good. Okay, so instead, we must have that the sine of Ka is equal to 0. So the way that a sine can be equal to 0 is if the argument of the sine is an integer multiple of pi, right? Because if we have the sine of 0, it's 0. The sine of pi is 0. The sine of 2 pi is 0. Okay? So we could say we must have that Ka is some integer multiple of pi. Okay, so n is an integer. Okay. Just to make sure, you're all familiar with angles in radians like this, right? Okay, the pi radians is the same as 180 degrees, okay? Meaning half of the way all around the circle. Okay, so we are learning something now that, up until now, we thought K could be any number. Now we see K can only be a certain set of specific numbers. Okay, so if we want to solve for K, that is n pi over A. Okay, I'm solving for K. I'm not solving for A, right? Because A is like an input parameter to this problem. A is the size of the box. I can't solve for that. Somebody tells me the size of the box, it's a 1 centimeter box or something like that. So, but I can solve for K, okay? And so I can see there is a set of allowed values for K, a discrete set, which I could call K sub n. There's a discrete set of allowed K values. Okay, so so far we've said n is an integer, all right? Now, what kind of integer, right? I mean, could it be positive, negative, 0, right? Well, let's remember that we have now a set of solutions, right, where solution number n is some coefficient times the sine of K sub n times x, okay? Which means a coefficient times the sine of n pi x over A. So we ask, can n be a negative integer? Well, if we put in a negative integer, then we would get, psi of negative n of x is a sine negative n pi x over A. But the sign of a negative number is just the negative of the sign, right? So that's negative a sine of n pi x over A. So this is just the negative of the solution with a positive value of x. So we could say, based on this, that psi of minus n and psi n are basically the same solution. except for an overall sign. The overall plus or minus. So that means, in particular, they have the same probability density. And they have the same expectation values. So there's no need to include the negative ones along with the positive ones. It's the same thing, okay? So therefore, we'll say n not a negative integer. How about 0? Can n be 0? Okay. Well, we have that kn is n pi over a. So k0 is just 0. Okay. So the solution psi 0 is a times the sine of 0. Oh, well, that's just 0. That's not a solution. It's not normalizable. It's just nothing. Okay. So based on that, we could conclude that n is a positive integer. Okay, so we have n equals 1 or 2 or 3, etc. Dot, dot, dot. Okay, so kn is equal to n pi over a. The time-independent solution is psi n is a sine n pi x over a. And there's an energy, okay? The energy is related to k. You might or might not remember, but this is how we defined k way back somewhere, way back here, right? We have this equation which relates k and the energy. So let me copy and paste it because I need it now. Okay, so we copy this. All right, and now if I want to paste it, I don't know, over here. Aha, okay, good. So that means k is related to a. Okay. No, k is related to e. Haha, k is related to e. So I can solve for e, right? So we square both sides. K squared is 2me over h bar squared. Okay, so E is h bar squared k squared over 2m, and k has to be one of these things. Okay, so there's an energy for state n, that is E sub n is h bar squared over 2m times kn squared. So that is h bar squared over 2m. And then n pi over a squared. So that makes n squared pi squared h bar squared divided by 2m a squared. So that's the energy of state number n. Okay, we're making good progress here. So we have the time-independent solutions. We have the energies. How about the normalization? Okay, let's say, what about the normalization? Right. So that means we want to know what is the integral from minus infinity to infinity of psi star of x, psi of x dx. Okay. So that is the integral from minus infinity to infinity. Let's see, so I'll go back to this thing. Okay. So that is, the complex conjugate of the solution. So A star, because A might be complex, sine kn(x) times A sine kn(x). The k is real, the x is real, so the sine is real, dx. Right? So this gives us, let's see, I'll factor out the A star and the A. That's the absolute magnitude of A squared. And an integral. Oh, what are the limits? Ooh, here, I should say something about the limits of integration here. Remember, psi, we've solved for psi inside the box. Okay, we've solved for psi inside the box. So psi is equal to this sine function when x is in the box. Psi is equal to 0 when x is not in the box. So that means in these limits of integration, I shouldn't really be integrating over minus infinity to infinity. I should just be integrating over the box. So from 0 to little a. Because psi is equal to 0 everywhere else. So now I just have the integral from 0 to little a of the sine squared of n pi x over a dx. So this is an integral that we can do. The easiest way to do this integral is that you can remember that the average value of sine squared is a half. The average value of cosine squared is also a half if you are integrating over some full number of cycles, which is the case here because n is an integer. Okay? So this is 1/2 times the size of the interval, which is a, little a. Okay? So this integral is the absolute value of a squared, big A squared, times little a over 2. And this normalization integral is required to be 1. Therefore, we can solve for the absolute value of A. So the absolute value of capital A has to be the square root of 2 over little a. Now, capital A might be positive or negative. It might even be complex. Okay, we don't know. but we can always just choose it to be positive. So let's choose A to be positive. So that means A is the square root of 2 over little a. Okay, so if we have that, then we know what is our time-independent wave function. For any particular integer n, we have our time-independent wave function is the square root of 2 over a sine n pi x over a. And we'll say for n is a positive integer. So this is our time-independent wave function, okay? Now, what about the time dependence? Well, we know that if we have one of these separable solutions, then the time-dependent wave function is the time-independent wave function times an exponential factor, right? E to the minus the energy, so in this case, E sub n, t over h bar. And we know what E sub n is, okay? We know that E sub n is this n squared pi squared h bar squared over 2m a squared. So that goes in there. Okay, so this is a list of the separable solutions. These are the separable solutions. The general solution has to be a linear combination of these things. So the general solution, we could say psi general of x and t has to be some combination of the special ones. So a combination, a sum from n equals 1 to infinity of some coefficient Cn times the special solution. So times this thing, okay? So that makes square root 2 over a sine n pi x over a exponential minus I e n t over h bar. Okay, so these are, the sequence of steps that you go through to solve Schrödinger's equation. So any solution of this form with any coefficients is guaranteed to satisfy Schrödinger's equation. Okay, so it satisfies Schrodinger's equation. Check. It satisfies automatically the boundary conditions because each individual solution satisfies the boundary conditions, and we're adding them up. One thing I haven't talked about yet is the initial conditions. I want to talk about that later. I don't want to talk about that yet, okay, but I will. Before I talk about the initial conditions, let's switch to Mathematica and see some examples of what these solutions look like. Okay. All right, so I go to Mathematica here. Whoops. And I want to share that. Okay. Wait, I'm just looking now. I see there's a chat. Brian was chatting something about the sine function. Brian, what were you saying about the sine function? I must have missed it when it came along.
I was just, when you were talking about k sub a equaling 0, how sine of negative x would equal sine of x.
Right. Sine of negative x equals negative sine of x. Right.
Yeah,
right.
That's what I meant.
Yes. Did I say it wrong? Or
no, I was just saying it ahead of you.
Okay, so that's just a clarification for people. Okay, great, thanks. Yes, you can use the chat for that, or you can speak up out loud for that too. You just say, excuse me if I don't look at you on the picture. That's fine. Okay, so here is a Mathematica notebook, which I will be posting on the Google Drive for any of you who succeeded in downloading Mathematica before it became impossible, and maybe others of you later. Okay, so here first, there's a little bit of setup steps. Okay, so for my setup, I'm defining the energy E for state N to be this thing on the top. Okay. I'm using a lowercase e here because in Mathematica, the uppercase e is reserved for something special. And so I use lowercase instead. And then here is the time independent wave function. Okay. So this little bit of syntax means if you input an integer n and you input x, you get out this thing on the right side. So square root of 2 over a times the sine of n pi x over a. Okay. And then here is the time dependent solution. So you input n and x and t, and you get out the time independent solution times the exponential factor. So minus I, the exponential of minus I energy times time divided by h bar. Okay. And then the general solution would be a sum of some coefficient times special solution number n. And so for this particular example, I'm adding up n equals 1, 2, and 3. In general, you don't have to stop at 3. I could go to 300 or 3 million or whatever, but you know, here I'm just stopping at 3 for an example. Okay, and then just to make things plottable, you know, I'm just putting in some sample numbers where A is 1 and M is 1 and H bar is 1 in some units. right? If I wanted to do this in real physical units, I could put in the number for h bar in terms of joules times seconds, and then put in the mass of a particle in kilograms and the size of the box in meters, right? And that would work, but the numbers would just be hard to work with. So I'm just making it all equal to 1 right here. Okay, let's do an example now. Okay. So suppose we want to think about pure state number 1. That means special state number 1, separable state number 1. Okay, so for my example, I'm going to plug in that the first coefficient, C1, is 1. Coefficient 2 is 0. Coefficient 3 is 0. Okay, so what is left is just this business. Okay, so this is the solution, the time-independent solution. That's this sine pi x over a times the time-dependent exponential factor times the normalization factor, root 2. So I could plot this at some time. Okay. So here is an example of a plot. Okay. So if I plug in the time equals 0, then I get this plot for the solution, which is a real number. It's a sine of x. Okay, so it looks like it goes up and comes back down again. So here's one edge of the box. Here is the other edge of the box. And so this is the solution at time equals 0. Okay, what about if we look into other times? Okay, all right, so in future times, psi does not stay real. So there's this complex exponential factor. So the wave function now looks like this, where the blue plot means the real part and the orange plot means the imaginary part. So as we watch in time, we can see these two parts waving back and forth, right? But nothing is going anywhere. This is a stationary state, right? So here is the graphics that corresponds to the mathematical thing that we proved before, that this is a stationary state, okay? That nothing is going anywhere. Okay, so that means we can calculate the complex conjugate. Okay, so here's a complex conjugate. We can calculate the probability density, that is psi star times psi. And we see it depends on x, but it doesn't depend on time. It's stationary, okay, not depending on time. We can check the normalization. That is, we integrate this probability density over the range for x from 0 to a, and it's equal to 1. Good. That's the way a probability density is supposed to be. We can plot it like this, okay? So here is a plot of the probability density for x goes from 0 to a, so across the box. So there's a big probability to be near the middle of the box. There is a small probability to be near the edge of the box. Okay, are we good on that so far? Questions about that? Okay. I didn't make a movie of the probability density. If I had, it would have been a really boring movie because it's not changing. Now what? We can calculate averages, all right? So we can calculate the average of X, okay? So that is this integral sandwich of psi star times X times psi, okay? Conveniently, Mathematica does the integral for us, and we get 1/2. So the average X is right in the middle of the box, right? I've already put in that A is 1, so 1/2 is the middle of the box. How about the average of X squared? Mathematica can do that also. Okay, it comes out to be 0.28. Okay, so there's an uncertainty in X, which is 0.18 in these units where A is equal to 1. Okay. How about the average momentum? Well, we can make up an integral sandwich for that, okay? So that is the integral of psi star, then the momentum operator, so negative I h bar d by dx times psi. So we can integrate that where X goes from 0 to A. We get 0. Well, that kind of makes sense, right? Because this is a particle that's not going anywhere, right? The average of X is not changing. So it makes sense that the average momentum is 0. How about the average momentum squared? So I make another integral sandwich with 2 momentum operators in here. So negative I h bar squared times a second derivative with respect to X of this psi. I could do that myself, but isn't it nice to make a computer do the work for us, okay? And so this average comes out to be pi squared, okay? So if I want the uncertainty in momentum, that's the average of p squared minus the average p quantity squared. That comes out to be pi in these units where h bar is 1 and A is 1 and mass is 1. Okay, let's check the uncertainty principle for this solution. Okay, so we can multiply out the uncertainty in X times the uncertainty in P. That comes out to be 0.56 time in these units where h bar is equal to 1. Okay, that means it's 0.56 times h bar. Okay. So I told you that the uncertainty principle is that this thing has to be greater than or equal to 1/2 h bar. So yeah, it's a little bit greater than 1/2 h bar. So that checks out, right? This is consistent with the uncertainty principle. One more thing we could average, okay, is the Hamiltonian, the total energy, okay? So we could say, let's do the integral sandwich with the Hamiltonian operator in here. So negative I h bar squared over 2m times this second derivative with respect to X of our example wave function. That comes out to be pi squared over 2 in these units. Okay. What about the average of the Hamiltonian squared? Well, so I can put in 2 Hamiltonian operators here, right? And so there is, minus I h bar to the 4th power divided by 2m squared, and then the 4th derivative with respect to x. All right. It's really nice to make a computer do this work. Okay? And this comes out to be pi to the 4th over 4. All right? So the uncertainty in momentum is, excuse me, not momentum. The uncertainty in energy is the average of h squared minus the average h, quantity squared, that's 0. And that's what I was claiming before, right? That this is a state with some uncertainty in position, some uncertainty in momentum, but no uncertainty in energy. It has a specific value of the energy. Okay, so that's my very first example here in this Mathematica file of just pure state number 1. Okay, now I want to go on and do similar things for pure state number 2 and 3, and then to have combinations of these states. I'm kind of out of time now, so I will stop for today, and I'll do more with this Mathematica file in the class tomorrow. Okay, so let's stop for now and take a break, and I'll see you guys at 12:30 tomorrow. Of course, I'll stick around to answer any questions.